Federico, it's your session, so you direct it.
Yes, okay. So we've got our, welcome to this session on Networks Theory 3. So we've got our first speaker ready to go. So he's Sang-On Lee, and he's going to talk about hidden dependencies in weighted networks. So you can start your video.
Okay, thank you. I'll play the video and take the question later.
Yep.
Hello, I'm Sang-On Lee from Gyeongnam National University of Science and Technology in South Korea. It's my great pleasure to get a chance to talk about my work about uncovering hidden dependency in weighted networks via information entropy at the CCS conference. The paper is available on arXiv, so you can look it up for all of the details. I have to thank my precious collaborators who actually did all the heavy lifting. The motivation to study this problem actually went back to more than 20 years now when I was in high school. I'm hiding the identity of the high school because it's not quite an honorable story to the school. There was a theft case in our dormitory, and a teacher said, "You may think you are just borrowing your friend's stuff without bothering to tell him. However, if you think he's your friend but he doesn't think you are his friend, you are a thief." So it's a kind of an interesting way to express the situation. So I actually suggest you to think about this problem yourself. Is it possible to have a unidirectional friendship relation? And 20 years has passed, and we actually know that there is a directional friendship, especially in online world where we are virtually living in 2020. For example, on Twitter, you have this following relation, not just the bidirectional friendship relation. So this is my Twitter account, and my dear friend and colleague, Professor Jeong in University of Seoul. I follow him and he followed me back as a mutual friends. And of course, I follow the Complex System Society, who is organizing this CCS conference, and also the journal Nature, and also the CEO of Apple, Tim Cook. But in contrast to this mutual case, there is no reason, for example, this journal Nature follow me back, just the ordinary researcher. So this following relation explicitly implies the directionality. In contrast, you may think that Facebook is different from Twitter because usually you have friends to each other on Facebook, but it's not always true in fact. In reality, you are supposed to like your boss post on Facebook because of this kind of a social pressure. So maybe it's just the difference between explicit direction and implicit direction. So our main question is there any way to extract this implicit dependency between the two nodes in seemingly very bilateral relationship in a network? So I took the example. We have two nodes here. Both are denoted by index I here. And for the record, the number of neighbor or degree is the same for both cases. Both the left-hand side and the right-hand side has 4 neighbors. And even the strength, the sum of all the weight around the node are also the same. So in this case, if you only characterize this particular node with the degree and strength, you will get the same values. But of course, almost intuitively, you know that it's very different, or the nodes are situated in a very different circumstance. So clearly there is something different. Of course, this weight is quite homogeneous. If you look at the right-hand side, the distribution is very heterogeneous. So weight distribution is different. So of course, when we talk about the distribution, we have to normalize these numbers. If you divide each of these weight by these strengths, you will get this probability-like value called normalized weight. We denote this normalized weight by this tilde symbol here. If you think about this weight, for example, as a duration of phone call you make with all of your friends, this probability shows the fraction of time you spend with the particular neighbor of yours. So in this case, the node I distribute the phone call duration time more or less equally to all of the neighbors. But in this case, you spend most of your time talking to J or M. So we already see some asymmetry between the seemingly bilateral relationship here. Mathematically, it means that the Wij tilde and Wji tilde will be different. Even if we start from the undirected weight, Wij, because of the difference in this strength. So because of this, the normalized weight is intrinsically asymmetric because sometimes sadly, the importance of node J for node I and the importance of node I for node J are different in general. So to examine the asymmetry here, the first thing you can do is obviously you can just measure this simple correlation between this and this for a network. So to test that, we use two types of different data sets. The first one is the World Trade Web data between the nations, spanning like 50 years. So in this series of networks, for each year, the networks representing the trade volume between the nations. So that is the first data set. And second data set is quite different one, which is Annals of Joseon Dynasty. And in this network, the weighted network represents the edges between the people described in this historic document. The weights are defined as the number of sentences mentioning people pairwise together. So there are very different types of networks. So we will actually see the clear difference. So as I already mentioned, the first thing you can try is Pearson correlation between the normalized weight, Wij tilde and the Wji tilde, in both directions. So we call this mutuality. So large value of mutuality means that these two directions are more or less similar. And if the mutuality value is very small, that means that the relationship itself is quite asymmetry in terms of this relative importance. And both of the network I mentioned are timestamps. So we can actually track the temporal changes of this type of mutuality. So if you look at this, the first one, the World Trade Web, shows this pattern. If you look at this, compared to this degree correlation or the associativity, if you are familiar with the network science, shows drastically different behavior, especially on this 80s and 90s, potentially because of this, the collapse of the communism or the oil shock. But if you look at the mutuality value, they do not change that much. That means that the mutual relationship between two nations are relatively stable compared to these drastic structural changes over the course of these very large external changes. And of course, we need to compare this value to null model. So by null model, we mean we shuffle all of the weights for a given network structure. So the structure is the same, but the intrinsic correlation between weights will be completely destroyed. So if you look at the World Trade Web case, if you shuffle all of the weights, the mutuality is actually much larger than the reality. That means that the international relationships are intrinsically very asymmetric. When it comes to the trading relation, usually there is a big country economically and small country. Because of this severe heterogeneity in economic scale, usually the relationship is not that symmetric. And in contrast, in terms of the relationship between people in historical record, it shows the very similar mutuality, even if you shuffle all of the weight. So relationship between people in this historical document are much more mutual. So the next question or the next step is how to quantify this intrinsic directionality from this weight distribution. So our idea is to use the concept of information theory. If you go back to this example, as I already mentioned, this normalized weight has become the probability variable. In information theory, there is a very famous and also very relevant concept in statistical physics, which is Shannon's information entropy. So you can just measure this entropy value. And of course, this entropy measure represents the homogeneity of a weight around node I. This entropy measure has this scaling property. If most of its weights will be similar or uniform to each other, they will scale like log of the original degree. And if a single weight or a few weights dominate the entire system, the entropy goes to zero. So because of this scaling property, if we exponentiate this entropy measure, we will get this very nice property. So for almost uniform weights, this so-called effective out degree is reduced to this original degree in the case of the almost uniform weight around each node. For a single or a few weights are dominant, it will goes to one or very small value. So as you can already see from our naming scheme, this effective out degree is the effective number of important neighbor. So if you actually calculate the left-hand side, as we can expect, the value is very close to 4, covering all of the neighbor. And as we expect, this effective out degree is close to 2. And in practice, we can just taking up to the top k tilde neighbors in terms of weight. The important part is this, from node I. If we repeat this same exact process for all of node, we will have this sort of intrinsically directed backbone of this entire network structure. It's the emergence of a hidden directionality or hidden dependency from the originally undirected weight network. So to quantify the properties of this extracted directed backbone, we can come up with some characteristic measure like a relative edge density represent the how much of the original interaction is recovered, and the reciprocity, how reciprocal each of the directed edges. We apply this directed backbone extraction process for the World Trade Web and the Annals of Joseon Dynasty data. The conclusion is very consistent with the result from the mutuality value I mentioned before. For instance, in the case of World Trade Web, fraction of reciprocal edge is very smaller than the shuffled weight case. So it's very consistent with the mutuality result, because if we shuffle the weight, we got this larger mutuality than the reality. And also in terms of reciprocity, the randomized version shows the larger reciprocity. Again, this confirms our expectation, which is the international relationship is quite asymmetry. And if you just construct the directed backbone, you will naturally get this effective incoming degree as well. This effective out degree means the number of nations you consider as important neighbor. But this effective incoming degree means number of countries who think you are an important trading partner. So in some ways, this effective incoming degree represents the importance of your existence more in this whole trading relation. So if you look at the China and US case, you will see the very large development of China over the past 50 years. And we check the 4 representative cases here. So here the local reciprocity is a local version of the reciprocity. Number of neighbors you think as important, and they also think you are important, divided by this effective outgoing degree, the number of country you consider as important. And the attraction ratio represents the ratio between the countries who think you are important and the countries you think as important. You can see some interesting cases here. China, US, Canada, and India. They all have a very different trajectory over the past 50 years of the history. So in summary, we provide the whole framework to quantify the homogeneity or heterogeneity of weight distribution. And based on the information theory, we provide concept of effective degree to quantify the intrinsically hidden dependency. And I would like to remark that during the preparation of this talk, we got our first referee report. The referee suggested very constructive direction of this research. For example, the long-range path properties. Because if we start to analyze long-range path properties, we can actually suggest hierarchy over the entire system from the less influential node to the most influential node. That can be a real hidden asymmetric structure. And of course, the application to the dynamical properties like epidemic spreading, which is the most important topics of this year. So thank you for your direct attention. And if you have any question or comment, just email me. And finally, stay safe and wear a mask. Okay, if you have any question or
thanks for the talk.
Do we have time?
Questions? Yeah, we have time for maybe one or two quick questions. If people have questions, I guess you can unmute yourself and ask them, or type them if you can't speak, and I'll read them out. Okay, I'll start with one question then. Someone wrote very nice work.
Thank you. Thank you for the very interesting talk. So have you also considered networks which are intrinsically directed, like in trade we have export and import?
Yeah, actually that's a very relevant part. Actually, I skipped that part because of the time limitation, but actually we have compare our extracted directed relation to the original directional relation. And yeah, I don't have time to explain all the details, but it makes sense, and it somehow verify that our extracted directionality information is it's verified that we kind of recover this the original data set. So we expect more application to that.
Thank you very much.
Anyone else? Okay.
I actually have a question.
Yeah.
Hello?
Yeah, go on.
Okay. So there's many. If you take a bipartite classification or something, right, and you do a one-mode projection, so you get an undirected network. If you process that further to actually find some asymmetries, you can actually, for example, get these kind of significances on the links, which are often also asymmetric in very special cases. So in that sense, if you apply your method and you compare it to something like that, where you have two asymmetric measures, have you ever thought about comparing these kind of asymmetries where one may be a subject of like, sort of the links by themselves, and then the other thing may be something that is like, as a kind of assigned by some label or whatever. Like, for example, I'm thinking of teacher-student relationships or some other kind of hierarchy, like which you could verify or put into question. There's probably a large amount of systems where you could do that. Is that something you have ever thought about?
Well, actually, I'm not quite sure if that's what you actually expect, but we have our plan to kind of recover this the temporal sequence of the events based on this directionality information we extract. So yeah, in our preprint we don't have that goal, that purpose, that analysis yet, but that's one of the long-term goal of ours.
Okay, thank you, Ron. So what I meant is, like, sometimes you have asymmetry as a metadata, and you're mining it out of the system itself. So the question is,
yeah, that's precisely what we did. Yeah.
Okay.
Thank you.
All right, thanks for your talk. Let's move on to the next speaker, who is Zakariya, I think. Can you try and share your screen, please?
Yes.
Thank you. Yeah, perfect. Yeah.
Yes, we can see. Yes.
Yes, we can see. Are you going to talk live, or you got a pre-recorded video?
Yes, I'm gonna talk live.
Okay, so I'll give you a warning when you've got 3 minutes left. That's okay?
Okay.
So, yeah, okay. So our next speaker is Zakariya Ghalmane, talking about interactions between overlapping nodes and hubs in complex networks with modular structure. Please go ahead.
Thank you. So hello everyone. So this work is a collaboration between the University Mohammed V in Morocco, University of Lyon 2, and University of Burgundy in France. So the subject of this talk is how to characterize the relationship between the overlapping nodes and the most connected nodes in a modular network. And so as you all know, in the most of real-world networks, nodes are usually grouped into very tightly connected groups of nodes and sparsely connected with nodes from other groups. And these groups are called the communities. And there is actually two types of communities. The non-overlapping community structure, where each node belongs to just community, and the overlapping community structure, where nodes can belong to many communities simultaneously. So real-world networks are also known to have a heavy tail degree distribution. That means that the majority of nodes have a limited number of connections, while there is some nodes that have that are very high connected in the network, and these nodes are called the hubs. So our goal in this study is to characterize the relationship between the overlapping nodes and the hubs. Actually, we want to prove a new property that the overlapping nodes are neighbors with the highly connected nodes of the network. So in order to show this new property, we follow this methodology. So at first, we reveal the community structure of the real-world networks. Of course, if we don't have the ground truth data, so to do so, we use one of the available community detection algorithms. After that, we form the ego network of the overlapping nodes, which is formed from the immediate neighbors of the overlapping nodes. After that, we define also the set of nodes of the hubs. And finally, we can measure the similarity between the set of the neighbors of the overlapping nodes and the set of hubs by using one of the following measures: the proportion of CAM nodes, the rank biased overlap, the correlation, and the degree distribution. Sorry. So as I said before, the ego network of the overlapping nodes is simply the immediate neighbors of the overlapping nodes. After that, we can define the set of neighbors of the overlapping nodes, while the set of hubs is defined first of all by ranking all the nodes of the network according to the degree centrality. After that, we define the set of hubs as the top ranked nodes, such that the size of the set of hubs has the same size of this as the set of the neighbors of the overlapping nodes. So in order to compare the set of the neighbors of the overlapping nodes and the set of hubs, we used many real-world networks coming from different fields and sizes. As small networks, we used the Karate Club network, where nodes represent the members of the Karate Club and the edges stand for their their friendship. Les Miserables network, where nodes represent the characters of Victor Hugo's novel, and the edges represent their co-appearance. Dolphins network is another social network, and the Game of Thrones network, where nodes represent the characters of this series. This is all the small networks have relatively high density, while we used also some medium-sized network like Ego Facebook network, where nodes are the profiles in Facebook, and we used also the collaboration network with the small density, and we used also some large size network with very small density. So at first, we measured the proportion of common nodes between the set of the neighbors of the overlapping nodes and the set of hubs, which is simply the intersection between both sets. Here in this example, we have just the last members of both sets that are different. After that, we use this measure in real-world networks. First of all, we revealed the community structure using the SLPA algorithm. Here we represent only the small networks. Here we represent the tripartite representation of these networks, where the left column represent the overlapping nodes, the middle column represent the hubs, and the right column represent the rest of the nodes of the network. So as you can see, the overlapping nodes are neighbors with the majority of the hubs. In Karate Club network, the proportion of common nodes between the set of the neighbors of overlapping nodes and the hubs is equal to 77%. This value goes up to 81% in Les Miserables. It is 77% for Dolphins and 67% for Game of Thrones. We also used this measure in medium and large networks, and we found that there is a high proportion of common nodes between the set of the neighbors of the overlapping nodes and the set of hubs. We used another measure called the rank biased overlap. This measure is similar to the previous one. It measures the intersection between two sets while incrementally increasing their depth. So it takes into consideration also the rank of the nodes in both sets. So as a result, we found that the RVO exhibit very high values for all the the network tested in our experiment. So there is a very high similarity between both sets. We also used the correlation. We used Pearson and Spearman correlation between the set of neighbors of the overlapping nodes and the set of hubs, and we found that there is a very strong correlation between both sets. And we also studied the degree distribution of both sets of nodes, and here we represent also the estimated distribution under the Power law hypothesis, and we found that both sets have a very close exponent. So we can conclude that both the set of the neighbors of the overlapping nodes and the set of hubs have follow a Power law degree distribution with very close exponents. And we also, in our experiments, measured the influence of the neighborhood size of the overlapping nodes. So we found that by increasing the size of the ego network of the overlapping nodes, for example, if we take the neighbors that are 2 steps away from the overlapping nodes, we found that we have a higher proportion of hubs in these ego networks, so which is normal because by increasing the neighborhood of the overlapping nodes, there is a high chance that we have more hubs in the neighborhood. And finally, we measured also the influence of the membership degree of the overlapping nodes. And we found that the overlapping nodes with the higher membership degree have a higher proportion of hubs in their neighborhood. So, which is normal because when we have overlapping nodes belonging to many parts and communities of the network, there is a high chance that they are neighbors with the hubs belonging to all these different communities. So in order to wrap up my presentation, in our study, we try to prove a new property in real-world network with the scale-free property. We found that we proved that the overlapping nodes are neighbors with a very high proportion of the highly connected nodes of the network. We used actually a real-world data set from different fields and sizes, and we after that we compared the set of the neighbors of the overlapping nodes and the set of hubs using many measures such as the proportion of common nodes between both sets, the LVO correlation, and we studied their degree distribution, and we found that there are a very high similarity between both sets of nodes. So this study is actually already published in IEEE Access journal. So if you want to check more details about our study, you can go to this reference. Actually, our study shed more light on how communities are actually organized and may have many perspectives. So thank you for your attention.
Thank you, Zakariya, for the interesting talk. Are there any questions? If not, I'll start asking a question. So can you just explain a little bit again about, so I understood about the kind of overlapping nodes and the high proportion of hubs, kind of on a, I guess, a theoretical level. What is the interpretation of it, the fact that you have, you know, what does it tell us about the kind of real world networks that you studied?
Can you precise please the question?
Yeah, so, no, it's so, you know, you've been talking about the, overlapping nodes and the fact that they have a high proportion of hubs in their neighborhood. And so, and I think that's really interesting. What is the kind of implication for the real world networks? You know, what does this tell us about the networks? You know, what kind of, new information do we gain about these networks by looking at this?
Actually, the information that we gain is that the nodes that are belonging to the overlapping areas of the network that are that take parts of many communities are actually neighbors with the highly connected nodes in these communities. Actually, we also extend this study. We apply this study in how to find the backbones in a network. That the backbone is actually the essential parts of a given network. So we used this information that that the overlapping nodes are neighbors with the hubs in this study. Actually, by having just the list of the overlapping nodes, we can reach all the highly connected nodes of the network. So we formed our backbone just from this information. By taking the list of the overlapping nodes, we took their immediate neighbors, and we found that our backbone contained the highly connected nodes of the network and the thickest links of the network. So
thank you. Thanks. So there's another question in the chat. We have time maybe for a quick answer. So from Julia saying, if I quote well, the conclusion is that a node has a higher probability of being connected to hubs if it is an overlapping node with respect to a non-overlapping node.
Exactly, this is the main conclusion of our work.
Okay, thank you very much, Zakariya, for the talk. So we now move on to our third talk of the session with Bram.
Hi, how's it going?
Hi.
So I pre-recorded my talk.
Perfect. Okay. Do you want to try and share the screen? Yeah.
Yeah. Let me just share. Yeah. And can you see it?
Yes. Perfect. Great. So,
and if I share computer sound, hopefully this will work. And let me know if it's not working. If you don't hear it.
Yeah.
Cool.
Okay,
Thank you very much.
So our next talk is from Bram Siebert about the role of modularity in self-organization dynamics in biological networks. And you can go.
So welcome and thank you very much for coming to my presentation today. Today I'm going to be talking about how modularity can have a significant impact on the formation of Turing patterns, both in allowing them to form and in the final patterns that do form. First of all, I'd just like to say a big thank you to my collaborators, Malbor, Asllani, Cameron Hall and James Gleeson. And this work has been funded by the Irish Research Council and Science Foundation Ireland. In 1952, Alan Turing finally answered the question, how does a leopard get its spots? With his seminal paper, The Chemical Basis of Morphogenesis. In this paper, he laid out a blueprint for pattern formation. So, for example, how does a leopard get its spots, but also to try and explain how the scales on a butterfly form, or pattern, or zebra stripes. And it's all based on a nonlinear reaction diffusion system. Initially, this was all done on a continuous surface, on a continuous setting. And later on, it was extended, the PDE formulation was extended to lattices and networks by Mikhail Michailov, and also a lot by Asllani. So just to briefly go over some of the mathematical backgrounds of Turing theory, like I said, it's a nonlinear reaction diffusion system. So you've got UI and VI, and those are the concentrations of activator and inhibitor on node I of your network. You've got F and G, so these are your nonlinear, that's your nonlinear reactions. And again, you can use any model you like whatsoever, as long as it's nonlinear. So F is for the activator, G usually corresponds to the inhibitor. And then finally, we've got these diffusion constants, du and dv, and that's times the Laplacian, which that models your diffusion, times the activator and inhibitor on nodes J. So these systems must have a linearly stable steady state, which we call U star and V star, in the absence of diffusion. You always start from this linear stable state, and then afterwards you'll turn on your diffusion, so you make your diffusion non-zero, and then we'll see Turing patterns forming. And just for, I guess, pedagogical reasons, we're using the seminal Fitzhugh-Nagumo system, which is designed to model the firing of a neuron. When we originally started this project, we were inspired by neuronal networks because they were reported to be quite modular. And at the bottom of the slide, you can see the Fitzhugh-Nagumo equations. So, as always in our nonlinear systems theory, we linearize about our fixed point, and then we take our perturbation set equal to the Jacobian, and in this case, because we're a rectangular diffusion system, so it's a Jacobian plus the diffusion times the Laplacian. And in order to see whether or not our system is unstable, we need to look at the eigenvalues of the extended Jacobian. So that's J plus the diffusion constants times the Laplacian. And in general, this is only possible if the diffusion rate of your inhibitor, so that dV, is much higher than the diffusion rate of your activator. However, in real life settings, the diffusion rate of inhibitor is almost equal to the diffusion rate of the activator. Modularity, however, as I'll show later, will enable patterns to form in the case where dV is fairly close to du. And finally, as well, the solutions of the form as written there. And what's important to consider, what's important about them is that they also consider the eigenvectors of the Laplacian, and that will be important right at the very end. To help us understand what's happening with our system, we often will plot the dispersion relation. So we take the eigenvalues of the extended Jacobian and plot them against the eigenvalues of the Laplacian. In the continuous formulation, we get the blue curve shown on the left. When we discretize it as a network, we then get the red stars that overlay on the blue curve. So as you can see on the left, there's only a very small part of the blue curve that's greater than 0. So, and our red stars are nowhere near that. So there's no pattern going to form on our network on the right. The reason why there's only a small part of the blue curve above 0 is because the diffusion rate of the inhibitor is quite close to the diffusion rate of the activator. So it might be possible with a different network to get eigenvalues that will be greater than 0, so we might see a pattern forming. But in this case, with a small world network, we won't be able to get one. Well, if we rewire it as a modular network, so I've shown you the modular network is now on the right, and the dispersion relation is on the left, all of a sudden, in these black diamonds, the eigenvalues of the extended Jacobian are appearing much closer to the y-axis, and what's happened here is that you've got 4 eigenvalues of the Laplacian that are really close to 0. So the gap between the 0 eigenvalue and the next smallest eigenvalue, or the smallest non-zero eigenvalue, is called the spectral gap. And in this case, the spectral gap is much smaller because of the modular structure of your network. And now we've got positive eigenvalues of the Jacobian, and this allows the pattern that you can see on the right to form. Notice as well that the pattern is homogeneous within modules. So if you're in the middle module and you're blue, then you can be pretty darn sure that in this setting, all of your neighbors will also be blue. So why does the spectral gap close? Well, if we take on the left 5 disconnected Erdos-Renyi graphs, and we take them as a network, so your network consists of 5 disconnected components, then the Perron-Frobenius theorem states that there are 5 zero eigenvalues of your Laplacian. If you connect up loosely, if you loosely connect up these modules, then your 0 eigenvalues in your Laplacian become very slightly perturbed from 0. And this closes the spectral gap in the way that you can see on the right, and again we get another pattern forming. And this is why modularity allows patterns to form much easier than on a non-modular network. So it's cool as we can see lots of different types of patterns depending on which eigenvalues are positive. So you've kind of got these 2 groups of eigenvalues. You've got your first little group that are near the zero eigenvalue that are there due to the modularity, and we like to call those the modular eigenvalues. And then you've got the rest of your eigenvalues that are much further down your curve, and we call those the non-modular eigenvalues. If your modular eigenvalues are positive, like we've shown in the left-hand case, then your pattern is homogeneous within modules and heterogeneous globally. On the other hand, if you've got non-modular patterns being positive, then you can see the middle case here, where about 3 of our modules have become unstable, and there's a really heterogeneous pattern. And then the 2 modules at the top, there's not a whole lot of instability going on. So if you've got non-modular eigenvalues that are positive, you've got a really heterogeneous pattern. On the right, we've got, we call it kind of a hybrid case or a chimera case, where you've got a modular and a non-modular eigenvalue competing. And in this case, you'll notice that 4, so your outer 4 modules, are homogeneous within the module, and your central module is completely heterogeneous. That's because of the competition between the non-modular and the modular eigenvalues. Okay, but why do modular eigenvalues lead to modular patterns, or patterns that are homogeneous within modules? Well, if we plot we can look at the eigenvectors of the dominant eigenvalue of your Laplacian. So here I've plotted, and I've normalized everything. So I've plotted the patterns, so the concentration of the activator. And if I go to my next slide, I've now overlaid that with the eigenvector. And as you can see, the pattern follows the dominant eigenvector almost exactly. So on the left, you see that your eigenvector, it's segregated. It's sort of got, I suppose it's got 3 levels, really. And we can see that we've got 2 dark red modules, a blue module, and 2 orange modules. So your pattern is reflecting your eigenvector. On the right, we've got a non-modular case. And in this case, the instability is localized to a single module, which in this case is the central one, which is a little bit, or actually quite heterogeneous. And there's not really much happening on the outer modules. So we wanted to test our theory against some data sets. So here we're testing our theory on the neuronal network of a P. pacificus. It's a nematode. It's a cousin of the C. elegans. And for the non-weighted, undirected case, we can actually sort of see that there is a little bit of a modular pattern going on. You'll notice on the left that we've highlighted that there are 2 strong modules that are sort of segregated. So you've got this, your eigenvector is equal on these places, and your pattern is sort of following the eigenvector. And we've corresponded that on the right-hand side. We've sort of shown as well that you've got these 3 modules. You've got the central clump of neurons that are a little bit heterogeneous. We've also got a few communities on the top left and bottom right that have got equal concentrations of activator. It's even nicer in the case of this zebra herd. So here we've got a really strong module in the middle, and you can see that on the right hand side, that's all dark red. And there's this little clique. If you look at the eigenvectors in the top right, there's these 3 points in your eigenvector that have got the same value. And you can also see that reflected on the top right of the pattern, where everything is dark blue. So in conclusion, a modular structure is critical to the formation of patterns. The final organization depends on the eigenvector to the dominant eigenvalue. This work is funded by the Irish Research Council and Science Foundation Ireland, so big thanks to them. And this work has also been published in Physical Review E, and I've included an archive link there at the top of my final slide. Thank you very much. If you have any questions, I'd be happy to answer them.
So thank you very much, everyone, for listening.
Thanks for the talk, Bram. Are there any questions?
Yeah.
We've got time for 1 or 2.
Yeah, thank you. Can I ask a question?
Yeah.
Yes, please.
Yeah. This is Hiroki Sayama. Very nice talk. So one question I have is that is there the mathematical relationships between the size of each module that you have in the network and the characteristic distance of the spotty patterns that in the Turing pattern that you would expect to see in the PD version?
So the PDE version already is for a continuous domain, so it already doesn't really work on networks. In the discrete case, I actually don't know if there's a big difference between the size of the modules and really what happens if you have different size modules. Although I did do a little bit of checking with very small modules of say size 1, 2, or 3, and the eigenvalue for the Laplacian is still, there's a very small perturbation, and in your eigenvector it stays segregated.
Mm-hmm. Thank you.
Thank you.
Sorry, I was on mute.
I have a question.
Yeah. Oh, sorry. Yes, please go ahead.
I'm Nivedita, and I'm a professor in Delhi University. It was a very nice talk. I liked it a lot. The question was that have you some information from the other eigenvectors about modularity?
Yeah. So, I mean, there's kind of two groups of eigenvectors, and I hope you can kind of see them here. Your first group of eigenvectors will all be segregated, like on the left-hand side here, and all of your other eigenvectors, so the eigenvectors that are associated with your non-modular eigenvalues, I didn't check every single one of them, but I do expect them to all behave sort of like the one on the right, where the instability is localized in a single module, if that answers your question.
Thank you. Very
Thank
well.
you.
Yeah,
Thanks. There's a final short question from the chat. Someone's asking if the results also hold for a large number of nodes, say 1,000.
I have no reason to suspect why it doesn't hold for very, very large networks. I did check it on networks of size up to maybe 500, but the integration takes a bit of time on my slightly old Dell laptop.
Okay, thank you very much for your interesting talk.
Thank you very much.
Right, let's move on to the final talk for this session with Niklas. If you're here and
yeah, can you guys hear me?
Hi, yes, yeah, I can hear you. Yeah.
Great. Okay, let me share my screen.
Have you got a pre-recorded talk?
No, I'm going to do it live.
Okay, that's fine. Do you want me to tell you when you've got 2 minutes left?
Yeah, I have the time in my,
perfect.
presentation also, so it should
no
be
problem
fine.
Then.
Right.
Yep, we can see your slides. So our next speaker is Niklas Kitzmann, and he's going to talk about policy and innovation spreading on the global city network.
Yeah, thanks. So yeah, I'm Niklas Kitzmann. I'm a PhD student at Potsdam Institute for Climate Impact Research in Germany. And I'd like to present to you the first project of my PhD, which is a data analysis of how urban innovation, specifically ones related to sustainability, spread between cities. So I'm looking at this as a contagious spreading process on a network, which is a concept that's used for similar phenomena in many different fields. First to come to mind this year is obviously diseases, and I'll be using the language from like epidemiology literature, such as infection and contagion, even though it technically doesn't apply to my problem because it makes it much easier. But spreading can also be, for example, in norms and behaviors or opinions on social networks. It's very relevant to cascading failures, which we just saw in the plenary talk an hour ago. And it's also important for the spreading of innovations, which is what I'll be talking about today. Also important and interesting is the connection to social tipping processes, for example, in societal transformation towards sustainability, which was actually my original reason for looking into all this. So what's interesting about cities is that they're on the one hand prime contributors to environmental damage, but on the other hand also among the most affected. And another thing is that they look to each other to decide which kind of policies or innovations to implement. And so they can kind of be conceptualized as nodes on a global network that these innovations then spread on. Social science literature of innovation spreading also in cities is actually sizable, but there's very few analyses of city innovation spreading that are really grounded in network science, and this is what I want to attempt here. So the overarching question then is, do network effects play a dominant role in urban innovation transmission? This is going to be an empirical analysis where both the network data on the one hand and the potential spreading process itself are known. So The question is then just how well do these two match, and how well does the spreading process match to the network that it's potentially spreading on. So developing this methodology is the first project, and this is what I want to present here. And in the future, I also want to apply this methodology then to various other data sets. So the data sets I use here for developing this method are on the one hand, a flight connection network based on a flight route database. And on the spreading side, I look at the bus rapid transit system, which is a public transport innovation that was invented, if you can see my cursor, in the early 70s, and went through a period of rapid expansion between 2000 and 2016, which is what I'll be focusing on here. So to analyze the spreading process, I extracted a weighted network of city-to-city connections from this route database. And then to find a measure for the contagion effect, we defined infection, what I like to call infection pressure. So you can see the equation there. It's basically just the fraction of how many neighbors of a city in the network are infected, respecting the weights. And of course, this may change every time a city in the neighborhood becomes infected. So the question then is, how well does this infection pressure predict the spreading? On the right here, you can see the two histograms, one of all the infection pressures experienced in any year for all the cities in the time period studied. And in the bottom one, you see the same thing, but only for those cities that would then become infected in the next time step. So what I like to call successful infection pressures. And if we divide the two, we can get the yearly infection rate or yearly infection probability as a function of the infection pressure down here. We can call this a dose response function based on Dodds and Watt's seminal paper. Basically, we would expect this to be highly correlated. So high infection pressure causes high infection rate, and it is. The zeros on the right here, just to talk about it briefly, have much less statistical weight, and so we shouldn't pay too much attention to them for now. So the question is then, does this trend that we can see here actually mean that infections are caused by high infection pressure? Or could it be caused by other effects? For example, homophilic effects, where cities may belong to a certain group that is well connected internally. And if BRT then happens to be very suitable for cities in this group, this might reproduce the correlation in this dose response function from the previous slide. So we need a method to probe these kinds of effects. And what we're using here for this is the surrogate data method, which is a proof by contradiction hypothesis test that is designed to kind of investigate and also exclude specific correlations or features in the data and their causal importance. So how this works is, first we identify some discriminating statistic or measure of interest, in our case a dose response function, and then to test for a certain feature of the data. For example, if we want to check very basically, does the network actually have anything to do at all with which cities become infected? Or is this correlation caused by something else, with some artifact? So in this case, we construct a null hypothesis. We could say infections are not correlated with the network connections at all. And then we partially randomize our empirical data in a way that is consistent with this null hypothesis. So in this case, we would randomize which cities get infected, but keeping the yearly infection rate the same. So if there are a discriminating statistic is then significantly changed by this, we can reject the null hypothesis, and we have found some evidence for the feature F in the data, feature X in the data. So in this example, the dose response function becomes very flat, and the correlation is gone. But that example is kind of basic, so let's apply this to something a little bit more interesting. Basically, we want to know, is this spreading of this BRT, is this an infection wave rolling from city to city? Or is like a metaphor of a rising water level more appropriate, where it's not really a contagion process? So for a wave, we would expect infection times to be highly correlated, and then infection jumps along the network connections. Opposite of that, the null hypothesis would be cities' infection times are uncorrelated with the city's position in the network, so uncorrelated with the infection times of the neighboring cities. So to study this, we can randomize the infection times while keeping the identity of the cities that are infected on the network the same. And we get something like this. So what you see here is the black dots are the dose response function in empirical data from the slides before. It's the same information. And then in blue here, you see the average of 1,000 runs of this surrogate data. So it's 1,000 randomizations of the infection times. So this isn't, of course, completely flat. So it's not easy to reject the null hypothesis outright, since all the empirical data is still within the 80% range of what the surrogate data sometimes also shows. But the thing is, we're kind of glossing over something here, and that is the data points within each of the surrogate data sets, within each single realization of surrogate data, are not independent at all. If one is higher, we would expect the other ones to be lower, since there's always the same amount of cities that become infected. So averaging over this with this blue line destroys this information. And to solve this, we can just put a linear fit through each of the surrogate data realizations, and of course also through the empirical data. And it's important to do this weighted. So on the left side, of course, these points have much higher weight, because much more cities were in their underlying bins in the histograms I showed you before. And so this is where we can get this red graph out for the empirical data, and then we can histogram this for the fit parameter sets for the surrogate data, and it looks about like this. So on the left here, you see the red cross corresponds to the red fit line to the empirical data, and this distribution here is basically all the parameter sets of all the different surrogate data runs. And you can see that this is pretty clearly separated. So it seems very unlikely that the empirical data, this cross here, is from a distribution like this. Which means we can reject the null hypothesis in this case, and can say, okay, it looks like cities' infection times are correlated within each other or within their position in the network. And this provides us with evidence towards this infection wave metaphor. So a true contagion process where the infection is spread from city to city to city, correlated in time. Right, to sum up, we've demonstrated that the surrogate data method is an appropriate method for evaluating the match between a network and a spreading process on that network. And the process also showed that there seems to be this contagion pattern, contagion behavior in the transmission of this particular public transport innovation on the flight network. So the next steps here would be to measure the spreading parameters using a statistical model and log likelihood methods, and then apply the method to more varied data sets, which is something that I want to end on. It actually turns out that that network data that is granular to the city level is very hard to find. Also because, mostly because I think there's few institutions that collect global data on all cities and aggregate it for use. And so I'm always very happy for suggestions for any more city level network data that spans the globe. And yeah, so if anyone has any questions or any suggestions about data, I'd be happy to take those now. Thank you.
Thanks, Niklas, for the talk. If anyone has any questions or, as you said, I guess, suggestions for data, please.
I have a question.
Yes, please.
Hi, it's a very interesting research, Niklas. Thanks for your presentation. I have a couple of questions. Maybe you mentioned these things in your presentation, but I might have missed them. So you say you're looking at the network of cities, but probably maybe you may want to look at the relationship between cities and higher levels of government, because cities don't always make their policies on their own. They receive sometimes pressures from their national government, or if they're in a federal system, from their federal state level agencies, or sometimes they receive incentives to adopt some policies. That might be something you may want to take a look at. Also, cities have some political positions. If you are living in a city that is left-leaning, they might adopt certain policies. If you're living in a city that is right-leaning, they might adopt some other types of policies. And these differences in political views of citizens living in those cities might influence the way these policies are being adopted and implemented in those cities. And they might create some interesting results in spread of climate change policies within city level. I mean, these are things that you may want to look at, and maybe a regional data set might be easier to find and work on instead of a global one.
Yeah.
Just my 2 cents.
Yeah, thanks very much for those points. I agree that the regional data sets are easier to come by. For example, also for stuff like sister city connections, twin city connections, and this kind of thing. I want to briefly respond to what you said. The political context, I agree that that's a very a very important influence also. So this whole idea is kind of based on this idea of cities as active agents in sustainability transformations, where of course cities are still bound within their national context, but projects like this one, like specific infrastructure projects, specific municipal projects, are often at the of course reliant on funding from the national level, but their actual implementation is more decided within the cities. So yeah, like for sure, with the political leaning also, this kind of innovation is never going to spread to all cities. Everyone's not ever going to become infected, because it's just not everyone is susceptible because of political, but also because of infrastructure concerns. So of existing infrastructure. So this kind of political leaning is definitely yeah, a big factor in who actually then ends up becoming infected, that I didn't quite that this method of course doesn't quite get to.
All right, thanks again. So I guess the time the session is finished. So there's now a time for a break. I don't know if anyone has got any more questions. You know, you can maybe ask it to Niklas either here or during the break.
Yeah, I'm happy to stay in the, sorry, Federico, I'm just saying I'm happy to stay in the chat if anyone has any more questions.
Yeah, sure. No, that's fine. So yeah, that's great. If you want to chat more with Niklas, I just want to say thanks to all the speakers for their interesting talks.